Welcome, everyone, and thanks for taking the time to join us. We're going to show you who we are, what we do, and especially how it can help the issues you may have in your space and or allow you to create some really engaging experience. We'll have a Q&A session at the end. You can post your questions while we go through our presentation, and we'll try and get your your questions answered then. My name is James Bobel. I'm the sales manager of North America for HOLOPLOT. I have spent a number of years in the audio business chasing the magical technical ultimate of loudspeakers, and have enjoyed my journey and my life doing such. And when I came across HOLOPLOT and had the opportunity to join this team, I was more than thrilled to do so. We're breaking ground, changing rules, and inventing new ways to do things, and we're really excited to show it to you.
And I'm Mike. I'm a senior applications engineer with HOLOPLOT. I've been with the team a little over 2 years. I come from an acoustical consulting background. I've loved music my entire life and loved enjoying solving problems with sound. So the opportunity to be at HOLOPLOT and work with our product and show it to new people, it's been a lot of fun for me.
And HOLOPLOT ourselves, the company started out in a garage in Berlin, very humble beginnings. In about 2011, as a small team of researchers, working to prove theoretical concepts in sound, things like 3D audio, beamforming, and wave field synthesis. All these things had been well written about and discovered, just not put into practice in an actual product. Recently, all the work had been to create a prototype of an actual speaker system that did all of those things. That caught the attention of the people at MSG who were building the Sphere, and they invested in the company. That led to the development of a large format concert-ready sound system, and allowed us to carry on and develop some more. We're now a team of about 130 employees from about 33 countries from all over the world, and we're growing. And we're headquartered in Berlin still, and we have a US office and distribution center in Las Vegas, Nevada. Um, 3D audio beamforming enables control over sound propagation better than any other conventional system, and it reduces unwanted reflections and improves speech intelligibility. And what that means for projects is a new way to make sound work in spaces where we need to do it. Unmatched sound control, really concealable, and increased flexibility. And then all of that controlled by a really, really powerful software that allows us to be flexible in operation and recall things like presets. And all this, the goal of this is all about control. We've been doing sound in public spaces for about 100 years, and it's led to all kinds of developments to increase control and to be able to scale sound. Started out in the earliest days by putting horn walls onto a transducer to amplify it and control it, and then combining those sources into multiple enclosures or multiple device enclosures, and being able to gain system size and control based on their orientation and how many you use. That was very effective in line array technology, let's say, in controlling the sound from front to back. Gives you really good control and really good control over distance, but doesn't really do very much for the horizontal. And in rooms, the walls being in the horizontal plane, generally, that's a pretty important thing. And one thing that the matrix array did solve is the ability to build your system in the direction where you need the control. not just in the vertical, but is in the horizontal as well. And if you can look at what we've put up here in the screen, just a standard line array doing a really good job front to back, but not unable to control much of the content in the horizontal. So we can see in the second image where we have a matrix array placed and we've tightened up the sound, the coverage pattern. And you can see in the grade of blue to orange how much and how discrete that sound can be and how adjustable that pattern can be. And I'll hand it over to Mike to talk about some of the numbers and how those benefits can be really helpful into producing better sound.
Great. Thanks, James. Yeah, so we've got control now with HOLOPLOT technology. And when we're talking about how control actually benefits a project, we typically are first talking about the direct to reverberant ratio, right? So this means that we put less energy into the room reflections and more energy into the direct sound. And what this means is an improvement in intelligibility, right? We're going to talk about STI, the speech intelligibility metric. That's the industry standard metric a little later in this presentation. And you'll see that HOLOPLOT systems are achieving the best STIs that we've seen in the market to date. So HOLOPLOT's got two main technology pillars that we're often talking about, and these are 3D audio beamforming and wave field synthesis. We like to think of these technologies as parts of a multi-tool, right, for solving acoustical challenges, architectural challenges, and then for creating unique and engaging experiences. So the technology can be used for very traditional audio coverage use cases, but the level of control that we've got now means that we're still discovering new use cases for the types of audio coverage that we can create with this new technology. And we'll show some of that here. So starting with the 3D audio beamforming side, we can define coverage areas of any shape and size in our software, and then use HOLOPLOT's optimization algorithms to create a specific coverage pattern from a matrix array that's going to target however many of those areas we decide, right? So these coverage patterns, we call them beams, right? We work with beams in HOLOPLOT software, and each beam is then assigned to an audio input channel. So these beams that are created by the algorithm are optimized to achieve uniformity in both spectrum and level over a target area. So they compensate for distance, they compensate for unique audience shapes, they compensate for the environmental conditions, and any other parameters that you set for these beams in the software. And that allows us to overcome challenging venue architecture, challenging aesthetics, and also means that we can deliver unique audio features that aren't possible with conventional systems. So an example of that is our systems are actually capable of producing content in multiple locations from the same array. So this unlocks things like multi-content or multilingual coverage, which if you've come to a HOLOPLOT demo recently, you'll likely have heard our example of a multilingual worship band. So we have a stereo playback of just the instrumental track, and then out of our central array, we create 3 discrete zones of coverage. And those are all 3 audio inputs, and we have a recording of a vocalist singing this worship track in 3 different languages. So as you walk through those 3 discrete coverage areas that we've created, you're stepping into a worship service that is in a different language. And so that's something that's never been possible before in one space. And that's the level of control now that we've got. So those 3 slides were kind of speaking of 3D audio beamforming. This slide is kind of talking about wave field synthesis. So we create virtual sources using wave field synthesis. Sometimes we call them focus spots. So what we do here is define an origin point for a virtual acoustic source. So this can originate either behind or in front of an array. And then the drivers are used to create the propagation of that virtual source where there is no speaker. And so as an example, you can place a virtual source out in an audience just in front of a listener, and they'll perceive that source as being just right in front of their face, even though the array can be 100, 200 feet away. And so this focus point can literally be the size of a single person, and you can create personalized experiences for multiple audience members at a time. Um, so really, wave field synthesis is a brand new tool in the toolbox for sound designers, where they can play with proximity and perceive distance to sound in really precise ways. So that's just a quick intro to what our technology is and what we're achieving. We'll talk about the products quickly. So there's two products in the HoloPlot ecosystem. There's the X1 and the X2. So the X1 range comprises two variants. There's the MD96 and the MD80S. Here they're shown with their grills off. So X1 modules are intended for high SPL applications where high fidelity and sound control are required. The modules are arrayed in a matrix, so vertically and horizontally, so that you can provide beam control in all dimensions. The modules have all of their amplification and processing built on board. They run the HoloPlot operating system, and that's remotely accessible from software. So you can download software updates. You can also monitor the system remotely and support it remotely. Here's an image of the multi-layer driver arrangement within an MD96. So these are all the drivers that get individually amplified and controlled to create the different coverage patterns and beam shapes that we talked about just previously. So there's 78 soft dome tweeters, 18 low frequency cones. And so that's the MD96. And then we can look at the MD80S. It's a very similar arrangement for the high and the mid frequency section. And then you can see we've tucked the 18-inch subwoofer behind in a ported enclosure. It's a feedback controlled subwoofer using pressure sensors, so it provides higher output and lower distortion. So these two modules get combined into arrays in any shape and size, and that's how you start to build a HoloPlot system with X1. Then we've just recently launched X2. Within the X2 line is the MD30, 30 meaning 30 loudspeaker drivers in a single cabinet. So this product's optimized for speech and for multi-content applications, and it achieves next level performance for speech intelligibility, particularly in spaces with challenging acoustics. It's slimmer and lighter than the X1, so it's ready to integrate smoothly into the aesthetic profile of an architecturally sensitive venue. It runs all the same beam processing and remote health software as the X1 modules, and is powered using PoE, PoE++. So all the audio and control data and power to the module runs over a low voltage category 6 cable. It comes with a frame for install. So this is just to give you a sense of the scale and the install method for X2. The module slides into that frame. And so all the tech is concealed in the frame in a clean package. Okay, so we looked at some products, and now we'll go through a few case studies here. This is the St. Hedwig's Cathedral in Berlin. This is the first house of worship install for X2. It's a very historic church, and they had a number of design considerations that we overcame to give a best-in-class audio solution. So this install was part of a full refurbished project for this historic theater, this historic cathedral, rather. And you can just see how beautiful the room is and how minimal the finishing are. So visual integration was the utmost importance for this project. They did not want to see any loudspeaker arrays, and we ended up concealing them behind acoustically transparent panels, which we'll see in a later slide. You can also see just above in that image, there's a dome. So domes for acoustics are essentially the worst shape that we can work with. And in this space, the mid-frequency reverberation times were up around 6.5 seconds. And in a space where the spoken word is the only thing that really matters, acoustical treatment is also not an option here due to this, the historic nature of this room. So they turned to HoloPlot. The system that we designed with them, it had to be hidden, and it had to provide very direct sound energy to the listener area. So we tried to minimize the number of sources, as this is generally a benefit in terms of minimizing multiple sound arrivals and getting the best intelligibility. So we placed a central array. It's a 6x3 of X2 that was mounted about 75 feet up in the air, and it's above the chapel door. And then there's two smaller 2x1 arrays that are covering kind of the outfills. And you can see there the complex shape and curvature of the coverage area that we're trying to hit with these arrays. So this is the shape that was fed to our algorithms and then generated the beams that were optimized for level and uniformity in that space. The results of this project, we achieved the architectural integration goals, being able to place the arrays behind these panels that you can see in the image here. On the right side is the perforated wire screen, and on the left is the 6x3 X2 with the grills taken off. The coverage was optimized for the areas that needed sound and avoided sending energy to the altar or to the rest of the room. And then the coverage areas were also set to accommodate seated and standing positions. So it's a coverage that actually works for both positions. And then we'll look at some simulation results here. So this is, you can see on the left, the target zones from the main array are in green. The fill array target zones are in yellow. And then the areas that we were actively avoiding are in purple. On the right, you see an STI map, speech intelligibility index, for those covered areas. See, we average about a 0.52 STI in that room, and that's with a 6.5-second reverberation time. So this is pretty astounding. All the conventional distributed point source systems that had been designed previously for this room couldn't crack a 0.45. And if you know STI, the index from 0.45 to 0.52 is a dramatic improvement. So, with the sight lines and the architectural limitations of this room, this is a pretty incredible achievement. The next project we'll look at is in Cairo, Egypt. This is the largest mosque in North Africa. It's when I say large, I mean large. It's 10,000 square meters. That's about 2 football fields inside. And we cover this entire space with 9 array positions. We used X1 modules for this project. It again is another very acoustically challenging space. It's again about a 6-second reverberation time with a domed ceiling, lots of historical and minimal finishes around the space, and a hard place to try and do speech intelligibility with conventional systems. So we had a multitude of positions that were really unachievable with conventional technology. We were throwing about 90 meters in some spaces. We had control in the horizontal and vertical, as you can see in the images here. So, there's long oblique shaped zones and zones with a completely different aspect ratio, and the X1 processing can handle any of these zone shapes. So the architects were very pleased that we could place the arrays up high or up behind, again, kind of perforated architectural panels. And then we'll look at, again, an STI map for this project. Here we're achieving about a 0.6, and this coverage was optimized for a kneeling position as well as a standing position. So again, accommodating the use case of the space as the worshipers and the listeners in that room move throughout. So yeah, just another look at results for this. A key thing here was, again, acoustical treatment in this architecture was not possible. It was just unfeasible. So they needed a system that could achieve the best intelligibility. We were also able to use just 70% as many acoustical mounting positions or installations of the speakers. So that simplified the integration quite a bit. And again, did not compromise the architectural aesthetics of that room. Okay. So we've looked at some case studies, and now I'd like to jump into the software. So we've been talking a lot about how software enables our hardware and enables the solutions that we want to implement. So I'll jump over to HOLOPLOT Plan, and we're actually going to take a look at a few more designs with, I'll call them more modern churches, and we'll take a look at that now. Okay, I hope everybody can see this. So this is what I'll call a modern worship space, and what we've done to try and achieve both optimal coverage, but also a few unique capabilities. We've got a left and right array of the MD96, and then two outfills here. This is, some people may call this a rock and roll church. They wanted um, really high speech intelligibility and really high level in this room. And so I'll turn on simulation here and we'll go through a few of the beams that we've created for this project. So uh, out of the left main and the right main, we've got our stereo coverage, and you can see this is stereo coverage for a majority of the audience. So even this seat all the way over here is getting stereo coverage from the right array, and that's a unique capability with HoloPlot. Most conventional systems, the horizontal coverage kind of has a fixed dispersion. And if you can't get the arrays, if you can't stand within kind of where those dispersions meet up between your left and right, you're not going to get stereo content. But because we can control the level consistently in the horizontal plane, you get left and right image out of your main arrays, no matter where you're standing. Um, but a very unique use case that we found here was that we can actually create a mono coverage out of one of these arrays simultaneously with the stereo coverage. What this is going to do is going to kind of do two things. Mainly, you can have both of these input beams active at the same time. And so you can put your speech content through the dual mono system, and then you can put your music through the left and the right system. And so by separating uh, the coverage into the left and to the right zones and not having kind of that overlapping comb filtering of just a mono signal like you get out of a microphone, that's going to improve speech intelligibility and improve the coherence of a microphone, of the pastor, of the worship leader. But this can also do is enable the multi-content and multilingual use case that we talked about earlier. So the right half of this audience has got coverage. Uh, you could say that's in Spanish, and then the left half has got coverage. You could say English. And then, for the outfills, those get down mixes of everything because they aren't in, the location to receive stereo from those arrays. But you can see the coverage is extremely consistent for those locations as well. So that's a look at this sort of modern church example in HoloPlot Plan. This is a really easy software to work in. We'll jump over to another example. This is a beautiful church, Catholic church. It's got this fun octagon shape, and it's another room with really challenging acoustics. Every single surface in here is concrete. And the existing system was distributed point sources beneath people's chairs, and it just was not working for them. So what we looked at was using X2 for this project because it was a lot slimmer and easier to integrate into a very architecturally sensitive room again. So I'll turn on simulations again here, and we'll look at the coverages that we're getting. So we put an array on the left and the right position, and we've got a backfill as well. And actually, before I get into that, sort of a unique challenge here was this central position in the back would have been kind of our ideal use case, similar to the St. Hedvig's example that we looked at. But this is where the pipe organ is in this room, right? And so we did not want to interfere with that, both from a visual and from an acoustical standpoint. It didn't seem like a usable location for arrays. So what we were able to do is split the room in half, essentially. So we've got this right array covers this half of the audience space, and then this left array covers this half, right? And you can see the consistency of coverage front to back there. This is broadband DBA. And then the backfill fills in the back here. We also can create beams that when there is a live acoustic band there and they need a confidence mix, they've got that there. Or if the altar wants to hear some of the mix, we can create coverage for the altar as well if they want to hear the band back in their space. So yeah, we do onboardings for HoloPlot Plan all the time. And yeah, that's really all I wanted to share from HoloPlot Plan. I'll go back and share the slide presentation here. Oh, let me switch that back. Here we go. Okay, I think now we've gone through all that. It's it's time for a bit of Q&A.
I think the first question, Mike, that came through was um, about transmission loss through a surface. What kind of surfaces can and are best to use to put in front of your speakers?
That's a great question. Yeah, so we've kind of got a lot more experience, I think, than most manufacturers in such a short time placing our loudspeakers behind, what hope to be acoustically transparent surfaces, whether that's an LED screen or, a perforated metal. Really what's important is the minimum percent of the open area is the kind of the first step that we look at to see, is this even reasonable, right? So we don't ever really look at anything that's below a 25 or 20% minimum open area. What you start to lose is overall SPL capability and the spectral balance as you start to pass sound through those materials. A unique capability of HOLOPLOT is because we've got control in the horizontal and the vertical axis now, the sound transmission obstruction as you go through a perforated panel is not uniform in every angle of incidence. But we can uniquely compensate for those transmission losses at separate angles. We're doing this in Sphere. We're doing this in basically every project where we're passing through an LED or a perforated panel. So what this gives you is, again, the most consistent coverage that you're ever going to get when passing through a perforated material like that. Okay, I got another question coming through here. How do I reconfigure the system to switch between musical and speech content? Okay, so I didn't talk about this in the run through of plan there, but we work in presets. So every single system can have multiple presets configured for it at a time, and those presets can contain a list of coverage beams of different shapes, right? So I can have a preset that is just my stereo coverage, and if I want to change it to stereo coverage with a low shelf boost for music, I can do that. Or if I want to change it to mono coverage, that's just a click of a button in the control software to change between different presets on a system. All right, another question came in. What's an average system size for around about 500 people? James, you want to take that one?
Yeah, sure. There's lots of answers to that question. And the first one is that the matrix array is modular. It consists of pieces, and those can be put together in so many different ways to meet whether it's a functional need or an aesthetic need or just a physical need. And if you look at the three projects that we showed, all of them had really specific things that either that either made sense to build the system in a certain size and fashion, whether it was to get the appropriate amount of SPL, to get the appropriate amount of coverage in each dimension, or to hide and obscure it in a way that worked. In the last example that Mike showed, the specific location that may have been best acoustically wasn't available because it was taken up by a pipe organ. And which brings up another consideration that HoloPlot's really great at evolving with, is that that system can be made in many different ways, can be hidden in many different ways, and can be adjusted in many different ways. And I think if you've been in sound for a while, you've ran into that in just about every installation or design where the speaker guys don't get the say in where stuff goes a lot of the times. So the ability to have a system that can be configurable in many different fashions is very helpful. So there isn't an answer for the 500 people. We can do that with a small array or a large array. It would just depend on what we wanted our outcome to be, whether it was going to be full bandwidth, whether we have control issues in which dimension, what are the arrayable, riggable points, and what's going to be the issues with sightlines. So the answer is whatever we want to do and whatever the project needs.
And I'll
Do you
just
like that
expand
answer,
on that.
Mike?
Yeah, I'll
Yeah.
just expand on that a little bit. The St. Hedwig's example we looked at, that's about a 250 person um, cathedral there. The array quantity, the model quantities used there, what is that, 6 by 3 plus another
Yeah.
4. So that's 22 of the X2 modules. But again, as James was saying, those were sized and shaped based on the project parameters. Where do we need beam control? Where can the array live, right? So we've got the flexibility to achieve whatever we need to achieve because now we've got the modularity in the horizontal and the vertical axis.
Great. And there's another question in about when to use X1 or when to use X2. I'd give a specific answer. We X1 was developed and designed for full range, high output applications. X2 was focused at speech, but does a pretty good job at music too. So what we're finding in projects when we design with them is both generally work. X2 generally fits because it's a smaller module. It definitely fits in spaces where X1 has a hard time with its weight and size. And X1, of course, can get louder and more full range on its own. We've done designs with hybrid systems as well, where the X2 is doing the vocal center. It does a great job at producing human voice and being really, really even and um, inconsistent in the human voice. And of course, X1 can pretty much do anything from vocal to all the array of music that you would throw at it. But the choices are very definable and predictable in the software. And we also have not only probably the best prediction software that's incredibly honest and very functional, but we also have another software that we'll be launching soon called Create that will help you oralize your system. So we can listen to things like the directionality of beams, how tight and discrete they are, and audition some of those coverages virtually with a set of headphones and walk around your room.
Yeah, very excited for Create to launch. It's been, the people who've had early access to it for certain projects that we work on, they've saved a ton of time in their sound design, as they're preparing the stuff for projects like that. And it's a really great, tool to convince stakeholders, right, who can't read STI plots and can't, they don't necessarily understand the nitty-gritties of what an acoustical design entails, but if they can hear it themselves, it's a really useful tool for that.
Another question came up, where can we hear HOLOPLOT? Of course, the obvious space you can hear HoloPlot is in Sphere. It is functioning all the time, nearly every day of the week, with both movies and shows. But we also have a a demo system set up in our office in Las Vegas too. So if you'd like to come listen to it, audition things, and engage with us, we can give you our contact info at the end here and set something up. And I think that might wrap up the questions in the queue. If we've got anything else coming in. Anything else you wanted to add, Mike?
No, not right now. Really, the most important thing I would say is, if anybody's got any questions, the HoloPlot Hub is your place to go. That's our library of all the information of how to use our software, what the technology does, system design, best practices, right? So these questions of how big does a system need to be, that's a space where you're going to be able to find all that information, download our software. You can reach out to us there if you've got any questions on those things. It's a really helpful resource. And yeah, thank you everyone for coming.
Yeah, and we'll pause on this screen if you'd like to hit that QR code for any more info and engage with us directly. We'd love to hear from you. Thanks, and we'll see you soon.